Hi, this is Rahul. In this lecture, I am going to discuss one graph algorithm which is DFS, which is a searching algorithm. So we have two type of graph algorithm related to search. First one is a BFS, second one is a DFS. If you don't know DFS or BFS, I'll let you know all those things, how these two algorithms works. In this lecture, I will discuss only BFS, and if you don't know BFS, then you go to my previous lectures which I uploaded. You can watch it out that lectures, then you are able to understand BFS. I will explain what is the difference with difference of working principle of BFS and DFS. Right. Suppose you can see here we have a grid space where we objective is to search this treasure which is present in this. I have marked this cell by red marks, and you can see here right side also we have one treasure. Our objective is to find it out or search it out. Right? How do we actually do in these two type of searches? So in BFS, what we do, we start from any random point. So suppose we have selected this is a starting point of searching, right? What we do from this BFS, from this point, what we do, we go to first breath, right? We have went to the breath, and now we will figure it out next breath. Next breath we went, right, and then corresponding to next level of breath, in this way you can see we are expanding breadth in each levels of searching, you can see, and next level the breadth will expand like this. In this way we are moving forward toward these treasures. Our objective is to search these ones. So in BFS, we are moving level by levels, but each level breadth is expanding. But in DFS, in DFS it is little bit different. What is the difference? Here also we will select any random points from where we are start searching, right? But what we do here, from this point, what we do, we expand, we actually explore all the neighbors where we want to go, and one of recent explored neighbors we will move to exploring neighbors, right? And one of recent explored neighbors we will move to explore neighbors. Anyone we can search, we can select to explore next levels. You can see here over here how I am expanding this one, right, like this. From here we can expand like that, right? In this way we can, if we have selected this one, so in this way once we get this one, once we reach at this cell, at that moment of time, so we will stop. In this way, this type of searching depth, we are moving first depth, then to breadth. Here we are moving first breadth, then depth, right? This is the difference of searching of these two algorithms, right? In which is related to graph. In how DFS work in graph, let's see it. Suppose we have a graph, very small graph we have, and in this graph we have 5 vertices, 1 2 3 4 5, and set of edges we have 1 2 2 5 1 4. As you can see, 1 2 there is one edge, and 2 5 you can verify yourself whether this set of edges is correct or not, right? One notation, so what we use, g of v comma z, e to represent this graph, right? Now we'll see how this DFS work step by step, right? Suppose in the first step we start from any random vertex. You can see here we have selected this one as the starting point of exploring vertices, right? So the neighbors we will explore, right? You can see these two neighbors we have explored. You can say we will use one array, and I will tell you what the behavior of this array and what is the difference we will have as compared to in BFS we had. So we will print this one, and what we see, which one the vertices which are explored we will add in this array. You can see here we are also adding from the right side, or you can see at the end of array. So initially there was no array, so there was no element in this array, so that's why we have and 2 and 4, right? I hope this is clear. This is the first step. And next step, what we do, simply any these two were explored in the recent step. As we can select one of these two recent explored vertex. We will selected this one 4, right, and start exploring, right. You can see the 2 was already explored, so not need to worry about. And we just print out 4. And what we see, how do we actually selected 4? We will select the last element from the array. You can see in this array there was 2 element 2 and 4. From the last of this array we have selected 4, which was not, which neighbors was not explored yet, right. So we have selected 4 and explored the neighbors, right, like this. And this 5 was explored just now, so that's why we add this 5 at the end of array, right. This is how step 2 work. And next step, what will happens? You can see how many elements we have in this array. 2 elements. At the end we will, what we do, simply we will add this array. Sorry, we will explore the neighbors of 5 in this array. You can see here from 4. We explore this 3, right. We will add 3. Now one more things what we are doing here. Once we selected to explore the neighbors, at that time we remove the element from the array. You can see we have removed 4 and added 5. 5 is what? Neighbor of 4, which was explored just now. And you can see here also, if we have selected as 5 if to explore just neighbor, so what we do, we simply print it out and remove it from the array. And whatever the vertices which are explored, this step we will add in the array. This is how it look like, right. In the next step, what will happen, you can see from the end of this array we will select the vertex, the surrounding which was not explored. We have selected 3. You can see we will print it out and remove from the array. You can see 2 will be there. And you please notice this, what is happening from the end. We are removing and we are adding also from the end of this array. The two characteristics of this array. The difference in BFS, what we were doing, we were removing from the beginnings of this array, but we were adding at the end of this array. So the difference is in the DFS we are removing at the end of array, but in BFS we had two-sided. This was removal and this was adding or appending, right. This is the main difference, right. What is step 3? What is step 5? Sorry, what we'll do, what we see here, there was only one elements 2. Let's say explode all the neighbors. What we found here, all the neighbors of 2 which are already explored in the previous step. So that's why we do not add any element in the array. Now we see what we see here, array doesn't have any elements. What we found that all the elements of this graphs are explored. Now we see one thing I wanted to tell you, which is always asked in an interview or exams, that the array has 2 operations. What 2 operations? Inserting a vertex at the end, right, and popping out or remove a vertex from the end of array. Both operations, these inserting and removing, is performing at the end of array with the last element of the array. Suppose what I mean to say, array has 1, 2, 3 elements. Let's 3 elements we have. If we want to insert any element, let's say 5, what will happen? Array would become 1, 2, 3 and 5, right. What happens if you want to remove one element from the array? We will have array 1, 2, 3, right. These 2 type of operations we are performing. Because of this behavior of array, what we call this as a stack. Remember it. The array, if any array having this kind of behavior, or having these two operations which are specific to the positions we call as a stack. Now, the same things I am going to explain and again the what is the difference and how the working principle of DFS and BFS. This is a space tree. How these the BFS algorithm search the vertices, and this is another space tree for the DFS. The algorithm search the actual tree. You can see over here. We start from 1. Start exploring vertices 4 and 2. We explore from 4, and next step we explore from 2. Right. If you don't know, you go to my previous lecture. You can watch it out, the how the BFS works. Then you can easily understand how this tree was made of. Right. In DFS, the way the time steps, the vertices were explored, that starting in the initial times, t0, what we start from 1, and we explore the vertices 4 and 2. What we see, any recent vertices from any recent vertex, we will start from exploring. Yeah, you can see 5. Now the 5 was very recent which was explored. Now we will select any recent explored vertex to be explored its neighbors. So we select 5 to explore its neighbor. Now later on what we find, from start exploring all the neighbors of 5 2, what we find here, all the neighbors of 2 already were explored, so that's why we don't do anything. So this is how space tree of DFS is built up, right? I hope this is clear. Now we will move forward and see the how the algorithms we can write it out, right? So if you want to write algorithms, as I told you in this lecture series of graph, I will follow the adjacency matrix of representations, and based on adjacency matrix representations I will write all the algorithms and try to make you understand everything, right? Suppose we have a graph. I have taken same graphs, and if you don't know how to fill this adjacency matrix, you go to my previous lectures and see how this graph works. Sorry, how do we migrate this representation from the given graph, right? I hope this is clear. So we will take one stack. As you can see, I had taken one array. I call here it is a stack, right? Stack in the beginning, stack doesn't have anything, so that's why I initialize with 5, right? I hope this is clear. Now for each vertices I will mark in the beginnings no vertices were explored, so that's why I am assigning corresponding to each vertices in this explored array to 0. What it means, no vertices in the beginning is explored, right? I hope this is clear, right? Now this is the first step where we decide from which vertex we start exploring, right? This is the u, and we can have in this array either 1 2 either 5, any vertex we can take in this step, so we can fill it out, and this is the starting vertex from where we are going to explore the vertices, right? I hope this is clear. What is u is the random vertex from the set of vertices. Set of vertices as what? This 1 2 3, any vertex we can select, right? Now this is the main things what of backbone of these algorithms, what is happening. So until the stack is not empty, we repeat this process. This process is what? This is what? Exploring the vertices, right? Now you can see over here what we is a first step. What we do, simply pop the one element from the stack. The if you don't know how stacks works, I'll tell you. If a stack having 1 2 3 elements, in the pop step what will happens, the third will be returned to v becomes 3, and the 3 will be removed from this array. The array will becomes 1 and 2. I hope this is clear. Now We'll move forward and see others in this loop. What is happening? We will explore the neighbor of this vertex, right? We will explore what the neighbor of this vertex. We will go all the vertices of V is what? Capital V. Capital V is your set of vertices we have in this graph. And what we see in this matrix, suppose if we have taken this 3 and we go all the rows in this all the columns of this row 3, if we have selected 3, then what we see, if there is a s u2 w is what? W is representing all the columns, each columns. And what we say, if there is an s, what we have, there must be entry 1. And what we say, another things we check whether the w vertex was already explored or not. 0 means the vertex was not explored. So that what we do, if these two conditions are true, what we do, simply push the w vertex to the stack, right, as we were doing. What will happen here, if suppose 1 2 was already in this array, and we have explored w as a 5, what will happen in with post operations? A will become 1 2 and 5. At the end of this array we add this one, right? I hope this is clear. And we mark that the w is explored by putting like this, that, right? We will assign exp index at w to 1. What it means, it w vertex is already explored, right? We repeat this process until when stacks become empty. Do you know why stack will become empty? Because at any moment of times, at the end of this whole process, what we found, all the vertex, this instruction will make marked as explored. Once all the vertices get explored, then these conditions get false. If these conditions get false, we will continue popping out elements from stacks but not able to post anything, so that at the end of processings we will get a stack empty. At that moment of time, this loops get break. So that is our goal. So if we want to print array what is in this traversing, we can write here print a statement, and we can print this way. Which one? This way I am talking about, right? This is how this DFS algorithms work. Now we will move forward and see what the time complexity of this stack algorithms sorry, BFS algorithms. Let's see. So if we talk about this time complexity of this loop is what? Number of vertices in this graph, measure number of vertices, right? The crucial thing is figure out what is the time complexity of this one. You can see the number of elements which can be added in this stack, which are how many? We can add only these many numbers or number set of vertices we have in this graph, right? This much I erase these all those things, and I explain clearly right over here only, right? You can see over here, I will write over here the time complexity, everything's right. The time complexity, you can see up to here, that will becomes this one. A time complexity, how many is a this much time complexity we will compute it, right? First we look at the time complexity of this one. This one is how much? Order of V, right? Because we are going from all the elements of W, right? For what? For each popping out from this stack. So how many elements we are popping out from a stack? We can pop out elements. What is the number of vertices in the graph? So the number of vertices which are possible in this one, then is W. Then the time complexity would becomes the time complexity would becomes V cross V, right? I hope this is clear. In other way, you can see number of edges which are possible maximum in worst case, or I'm asking number of entries which can be become one, which is order of E. So either the time complexity would become this one, we max of we can have this one or this one. We can write either V plus E. In this way we can write. Both are correct, right? Why this is correct? I'll tell you. This is the time complexity, right? Order of V have how why I wrote, because if we have the disconnected graph like this, 1 2 3 doesn't have any s in this graph. So what will have, then we will have the times will take only order of V. We may start from this one, this one, this one, this one, and time complexity would becomes order of 1. And if we are visiting each edge while processing the array, and while searching the vertices which was our objective is in by DFS, then at that time we will have this much time complexity, right? I hope this is clear. If you find this lecture is helpful for you, you can share with your friend, and if you have any doubt you can comment it out. I will definitely respond you. So please like if you feel this is helpful for you. Thank you.